Welcome to the webinar Refractory Gold, Maximize Value at Your Site, brought to you by CIM Magazine and Glencore Technology. I am your organizer, Michelle Beacom, Managing Editor of CIM Magazine, and my co-organizer is Ryan Bergen, Editor-in-Chief of CIM Magazine. Just a little housekeeping before we get started. If you joined by computer audio, please make sure you've selected the computer audio button. If you joined with the phone audio, please make sure you've selected the phone button. And if you have any questions during the presentation, please type them into the question box under the question mark on your GoToWebinar control panel. The questions will be held until the Q&A period after the presentation. Thank you everyone for joining us today. Now I will turn the webinar over to Ryan to introduce today's presenter.
All right. Thank you very much, Michelle. Thank you, everyone, for joining. And thank you, Andrew, for joining so early in the morning from Australia. Yes, today's presenter. Andrew is a senior metallurgist working in the Albion Process Technology team at Glencore Technology. Andrew has extensive site experience at various smelting and refining operations, most recently at Copper Refineries Limited. He now works across the scoping and feasibility of projects for both greenfield and brownfield operations, assisting clients to tailor test work programs and engineering studies to assess the application of the Albion process for increased metal uplift of base and precious metals. And also, Andrew will be joined for the question period by Laurie McDonald, Senior Metallurgist at Glencore Technology. So with that, over to you, Andrew.
Thanks very much, Ryan. Thanks for everyone who's joined online to have a look at this webinar. So as I mentioned before, I'm based in Brisbane, Australia, so it's a little bit early for me, so please accept my apologies if my voice is a little bit croaky. But let's get started and let's talk about a little bit about refractory gold. I thought I'd start this webinar talking a little bit about some industry trends that we're seeing. So despite additional complexity of extracting gold when we're talking about refractory gold, I wanted to point that it still constitutes a notable proportion of reserves and measured and indicated resources across the globe. We can see that particularly in North America, surveys show that refractory resources and reserves still make up potentially about a third of all gold contained. When we then start to look at grades, we can also see in the surveys that refractory gold has a much higher grade than its non-refractory partner there. In the past, it seems that our industry has focused on extracting from the non-refractory deposits because it's free milling, it's easier to send it through those conventional CIL circuits, leaving higher refractory deposits in the ground. However, the survey is also showing that that trend is changing. Between 2015 to 2023, for the annual growth rate in the production of ores, we're seeing that the refractory deposits are starting to outpace its non-refractory ones, meaning that producers and sites were starting to recognize that there is this hidden value here, this locked value that should be unlocked, and despite its additional processing steps there. On the right is a curve that shows the all-in sustaining costs comparing refractory and non-refractory deposits. And I actually found this one very, very interesting for me because what the survey is showing is that for the all-in sustaining cost for gold, refractory on average was less than the non-refractory. So despite, an additional processing step that would be required to unlock gold in refractory deposits, it's showing that the cost is a little bit cheaper. Now, the survey didn't say exactly why. This is just me guessing, and please put in the comments if you disagree or if you think differently or even if you agree. But I'm guessing that because of the lower grade of non-refractory ores, the power required for the additional milling might be what's pushing up that all-in sustaining cost. That's just what I'm thinking. Okay, so refractory ores, we've established from the surveys that the value is there, but how are we going to take that next step and how are we going to extract the value from that? Perhaps that's okay. Let's take a little step back then. I'm talking a lot about this is refractory gold. So what is refractory gold? So deposits, when they're in the ground, they have multiple layers. Okay. When we're closer to the surface is weathered. It's been exposed to the elements for millennia and it's become oxidized. When we have an oxidized ore, then the gold is more accessible, and industry would call that free milling. However, as we move further deeper, all deposits will eventually go deeper and deeper to extract the target metal. We'll enter the transition zone. And so we're now going to start to see a little bit of both. We're still going to have partially weathered ore that's been oxidized and would still be considered free milling. But now we're also going to start to see some sulfides as well. So for gold, the gold would be locked in those sulfides, and that is what we would be considered to say refractory. Moving further and further down past the transition zone, all deposits then will eventually reach the primary sulfide zone. So in here, there's no more oxides, there's no more weathered ore, there's no more free milling ore, and all of the gold contained would be locked within the sulfides and considered refractory. So here we've got a very typical block flow diagram showing how we process free milling ores. So after primary milling, we can pass those oxide ores into a conventional cyanide leach plant. We can then produce our gold and sell it onto the market. However, what if we start then entering the transition zone? What if our deposit then now contains sulfides? What happens if we mill that and then send that through the cyanide leach plant? The consequence is that those sulfides will not, the gold contained in those sulfides will not be extracted in the cyanide leach plant, and the gold in the valley will not be able to be extracted. All of that gold will then go to the tailings plant. So one of the key questions that we get asked a lot in our team and at Glencore Technology is, we have our ore deposit, we've done some sampling, everything looks really good at first, but now we're moving further and further down into our deposit, into our operation, and now we're starting to see our recovery drop, and as a result, we're starting to see our revenue drop. So in this transition zone, if you don't do anything, and if you keep your processing circuit the same, you're going to start to see your gold recovery decrease as that gold locked in the sulfide ore remains trapped. It's not going to be able to be leached in your CIL circuit. So the goal for all operations, as we inevitably move into this transition zone, into this primary sulfide mineralization, is how we can keep everything in this green zone in here, despite changes in our deposit. We want to be able to maximize recovery and maximize revenue across the whole life of the mine. So when we have a refractory containing feed, or let me say this slightly differently, when we have a sulfide feed, for those of us in industry, we know that our first instinct is to float it. And that's absolutely what I would recommend we do. And that is to produce a saleable concentrate. Glencore Technology has developed a Jamison concentrator, which is made up of some technologies which you might be very familiar with, isomills for ultrafine grinding and Jamison cells for flotation. And absolutely, if you're able to, float a sulfide concentrate, produce a saleable concentrate, and then you're going to be able to sell that on the market and start to get a return on those sulfides. Typically, you'll still be in your transition zone at first, and you're going to still have some oxide material, and the tailings from your concentrator will then pass through your existing cyanide leach plant, and then you're going to continue to be able to produce metal in country. So I'm saying, you produce a sulfide concentrate and then you can just sell it, it's as simple as that. But of course, sometimes it's not. And as all metallurgists know, right, the answer to these things are often, well, it depends, right? Whether a saleable concentrate can be produced, it depends on the complexity of the concentrate. For example, do you have a polymetallic concentrate? Do you have copper? Do you have zinc? Do you have nickel? Do you have some other things in there which might make things a little bit more complex for the smelter you're trying to sell it to? Also, the presence of penalty elements as well. Are you having a high amount of arsenic in there or other deleterious elements, which might cause some issues? And something that's probably that has, existed for a little while now, but is becoming much more common, I guess, when we're reading the news, is the laws of the particular jurisdiction that your operations are in. Is it promoting in-country metal production? And obviously, your operation might also recognize that you might be getting more value if you produce the metal on site rather than selling an intermediate concentrate. If you sell your concentrate on the market, you still have treatment charges, refining charges, or TCRCs, and you're paying for someone else to recover the economic value of it. And something that gets overlooked as well, it doesn't get talked about as much, is it economic to transport the concentrate, especially considering your geopolitical environment? remembering that someone else at the smelter will be taking the full value of the metal in the concentrate, but you're only going to be paid a portion of it. So why should your operation take that additional step to produce metal on site and in country? So I've put some headlines in here on purpose. If you look at some of the data, you can see that these data are a little bit older. But what I'm wanting to show here is that, there are certain jurisdictions around the world which have started to or do have prohibitive barriers to selling intermediate concentrates. So they're either promoting or effectively forcing industry to produce metal in country. Right now, particularly if you're following the news, you'll know that there are certainly some countries right now and certain jurisdictions right now which are looking ways to promote and to force essentially some companies and some industries to stop exporting concentrates to other countries and to be more self-sufficient and produce metal in country. So it is quite topical at the moment. Okay, so this is the conundrum that a lot of clients come to us with. They're able to produce a concentrate, they've decided on a flow sheet, but they're not able to get good terms on selling it. They've got some prohibitive elements, or it's polymetallic and it's quite complex. It's prohibitive to do it because of the local jurisdiction that they're operating in, or it might not even just be economical to transport it. So they've decided that they need to treat it. So now we get to answer, how do we treat it? How do we overcome surface passivation in a hydrobet circuit when dealing with sulfides? What can we do about that? So our industry has lots of different options and lots of established options, and I just want to talk a few about that. We have pressure oxidation, also known as POX. So pressure oxidation is conducted in autoclaves. It's done between 10 to 30 bars, so in pressurized vessels, and the residence time is much shorter, between 1 to 4 hours. The temperature is quite elevated, between 110 and 220 degrees. Because of this more high intensity process, the way that it works is that colloquially, I can say that it kind of melts away the sulfides. It results in a high CAPEX, or capital expenditure, and a high OPEX, or operating expenditure, to keep the process going. It also is more complex, and you're operating a pressurized vessel at high temperatures as well, and then multiple unit operations are required upstream and downstream of the autoclaves in order to have a successful operation. Because of that, it also does require a more skilled workforce. It's something that is need to be considered depending on where you're operating. And there are certain safety requirements and safety expectations when you're working with much higher temperatures and much higher pressures. Another option is bioleaching, which uses bacteria. So bioleaching reactors are conducted at ambient temperature, but because they're using bacteria, the residence time is much longer for the process. We're talking multiple days, almost a week and sometimes. And because we need to keep the bacteria alive and we need to keep it thriving, the temperature is much lower and is much tighter. So we're talking between 45 to 65 degrees there. Once again, because we're talking with live bacteria, the process can be quite finicky and needs to be quite precise, and complex temperature control is required. You can imagine that in order to keep the bacteria alive, it needs to be kept within a very certain tight temperature band, and moving outside of that temperature band you can lose your optimization, and also the bacteria can die. Similarly as well, so the bacteria are used to a certain stable environment where we know that they thrive. If your feed changes, if you have unexpected downtime, if you have feed interruptions, that can really interrupt your process. And for bacterial leaching as well, if the bacteria does die for some reason, it can take days, weeks, months, depending on the conditions, to re-inoculate your process and to bring the bacterial population up to a certain level that you can then have an optimum process as well. And the last one that I want to talk about is the Albion process. So the Albion process was developed by Glencore Technology here in Australia, and it is quite an established technology as well. So what it does is it's a combination of mechanical liberation with the isomill for ultrafine grinding and chemical liberation in our oxy-leach reactors. So in the isomill, the ore would be liberated down to 10 to 18 micron, producing a fine and narrow particle distribution and producing micro cracks in the structure. Then in the oxy-leach reactors, we're able to dissolve away a sufficient amount of the host sulfide material. So we only dissolve as much as we need. And sometimes people call that cracking the sulfides, and that makes the gold more accessible and more amenable to downstream CIL leaching. So with a combination of these two technologies, we're able to proceed and maximize metal recovery before any sulfide reaction products could form a passivating layer. Yes, very good. Just taking a little bit of a closer look and maybe doing a little bit of a sum up of what we've talked about so far. So most operators will bring their operation online quickly, and they're going to be able to process their ore through the traditional hydromet circuit, which we're very familiar with, including a CIL circuit. However, as the mining progresses, we go further deeper into the transition zone, into more primary sulfide mineralization. We're going to start to hit those deeper sulfide-rich regions, and we're not going to be able to process it in that same flow sheet. Sulfides will generate a passivation layer in a hydromet circuit, which stops metal extraction. So what options do we have? We build a concentrator. Glencore Technology has a Jamison concentrator, and then so you're going to be able to separate a sulfide product, and that can be sold to third parties. But for the various reasons that we've discussed before, that might not be the best option, and we might want to start producing metal on site and in country. So we've got three options that are presented to you. We have the high CAPEX, high OPEX pressure oxidation, or POX, which melts away the layers of the sulfide minerals. We have a slightly more finicky and a longer residence time of the bacteria for the bioleaching, or we can have the albion process. So here we can optimize the grind size so that we're able to optimize and produce those microcracks, and then we can send it then to our oxy-leach reactors as well. And so that eliminates the impact of passivation layers, because of those microfissures, those microcracks, and then we're able to dissolve away a sufficient amount of that host minerals in order to liberate all of these different host metals such as gold. I just wanted to stress for all of these different technologies, we've talked about POX, we've talked about bacterial leaching, and we've talked about the albion process. Those three processes all on its own do not produce gold. All of these three steps are an additional step that is required in order to make sulfide or refractory ore amenable so that you can then pass it on to the downstream CIL circuit to extract it in that circuit as well. So I just wanted to reiterate that. Okay, so selecting the best process for your operation. Something that we have at Glencore Technology is an online calculator. So I've got a QR code if you want to get your phones out and you can take a quick photo of that. You can also Google albion process calculator. And what you can do is, all you need is a feed rate in tons per annum, your gold grade, your feed composition in grams per ton, how much sulfur you have in your concentrate, and then if you know any operating inputs, how much power costs, how much labor costs, you can put that in. Otherwise, it can be default. And what it's going to give you automatically and for free is an order of magnitude capital expenditure, or CAPEX. It's going to give you a whole mechanical equipment list for you to review, an order of magnitude operating expenditure, so you can present to your board, present to your directors, and you can show them these things. And it's going to show you our estimated staffing requirements, how much power is going to be required, how much oxygen is going to be required, and also reagents as well. Really some high-level things for you to be able to assess, and for you to be able to play through different scenarios as well and be like, okay, well, we're at this feed rate now, but I know in 5 years' time, we know we're going to have to hit that sulfide part of our deposit. What are things going to look like now? And then you're going to be able to play around and understand what's going on. So for the remainder of this presentation, what I wanted to talk through and walk you through is some different hypotheticals that I've done, and I wanted to show how the albion process stacks up against pressure oxidation. As with any scenario, we have certain assumptions there, and I've listed that on the screen. We can see we've given a nominal feed rate, 480,000 tons per annum, gold grade in the concentrate of 35 grams per ton. We have assumed some arsenic, presumably as arsenopyrite, and then a decent amount of sulfur as well. All of the operating cost inputs I've left as default, as you will when you check out the online calculator. Now, for this gold price, I have put a very conservative one. We know how crazy the gold price is at the moment, but I wanted to do something back to perhaps what we mentally in our head knew what the gold price was, rather than putting the very high and good numbers that we're seeing at the moment. For the assumption as well, if we sell it to a smelter, I've assumed that 95% of the value will be payable. The arsenic penalty for the treatment charge, refining charges I've put in there, and I've also assumed some transport costs. For the Albion process, for the recoveries, there are many papers that are published, and some of those papers I've put down the bottom and I've referenced down the bottom as well, but I've assumed a recovery of 96.2%. For comparison to POX, we have put a higher recovery of an additional 1%. So the reason for that is, as I mentioned, POX is a much more intense process. So it's at high temperatures and high pressures. And what it is it melts away typically all of the sulfides. So when you melt away all of the sulfides, you are able to extract all of the contained gold. With the Albion process, we pride ourselves on being able to optimize the grind size, and we only grind to as much as we need in order to get an economic amount of recovery there. But I am acknowledging that POX does have a high recovery. We have assumed a CIL plant, a CAPEX and OPEX. And then we have some factors in here. Like I said, these have been referenced in some papers from 2005 and 2012, and we can show that the factors of how much more POX costs for CAPEX and OPEX because of the higher intensity, because of the higher pressures and then the higher temperatures and the more complex control. If you're interested, something that I read early in the year is there is a more recent paper. It was done by a Michael Davis and an Adam Bird from Mindscope, and they presented it at a conference here in Australia called MetPlant in Adelaide. And it was actually a very balanced overview. It was a very nice read, and they give certain case studies comparing these three technologies and giving a great overview for refractory gold and just showing where each of the technologies excel. So if you're interested in that, please put something in the comments, reach out to us, reach out to me on LinkedIn, and I'll see if I can get you a copy of that paper because, yes, it's very good. I highly recommend. Okay. So this is our base case, and we can see here, we can see that using these assumptions, our base case, we have that amount of revenue per year, 825 million USD. If we then decide we're going to produce metal in country and on site, we're going to have additional revenue. We can see for the Albion process, an additional 110, and with the higher recovery, POX will give you an additional 120. These are the nominal CAPEX and OPEX, including the CIL. You can see here that the Albion process starts to look much more attractive, which is with its atmospheric leaching and with ultrafine grinding there on both CAPEX and OPEX. And then some high-level financials here. You can see what the payback period looks like. It looks a little bit better for the Albion process, got a positive NPV, and the internal rate of return at 10 years is all looking pretty good as well. But for those who worked in the industry a long time, we know that, this nominal gold grade that we see on the website is not always the case, and things always change, right? So initial assays are not representative. We've now hit a low-grade part, a low-grade zone. What's going to happen to our process if we proceed and produce metal in country, but our gold grade drops 15 grams per ton? With a drop in the gold grade to 20 grams per ton in concentrate, our revenue is going to drop, so our base case is going to drop. The amount of additional revenue is also going to drop as well, but the CAPEX and OPEX is going to remain the same. And then we can see here that the payback period starts to change as well. However, the Albion process is a lot more resilient, I would say, than POX here for this particular scenario. Despite the increase in the payback period and the slightly lower NPV and the change in the IRR, we can see that for pressure oxidation, when we start to drop the gold grade, that the NPV starts to go a little bit more negative. This one's very topical at the moment when we start talking about freight charges. I believe it's not happening just in Australia and Canada. It's happening all around the world. We're all worrying about freight, and it's not just mining and industry. It's all around our lives. What happens when the freight costs increase? What happens when diesel goes up? What's going to happen to our costs? What's going to happen to our operation? So we can see in here, these are I won't go through all of the numbers again, but you can see how an increased cost, the Albion process is still a very attractive option there with the payback period. However, with pressure oxidation, when we start to put a little bit of pressure, per se, we start to pull a couple of levers against it, we can start to see that NPV is still remaining slightly negative. And the last one I want to talk about is deleterious elements. So we start talking about penalty elements. In this case, if you're producing a pyrite concentrate, it's often associated with arsenopyrite. And so that's very common and happens. A lot of clients have seen that, and a lot of gold people will see that as well. What happens when we hit that term and we're going to double the amount of arsenic we have in the first 3 years, we're going to have double the penalty. So this has the biggest impact on when you're trying to sell this concentrate on the market. So our base case, that's where we're going to see the biggest change there. And we're going to see that drop significantly as you pay those penalty charges. However, if you've produced metal in country, both for the Albion process, or if you choose a pressure oxidation, your process should be able to ignore the effect of arsenic and be able to produce that down to an environmentally stable form. And you'll be able to see that for both options in this case, the payback period relative to the concentrate sales, because it's so low, you're going to be able to recoup the CAPEX much faster relative to that one. Okay, so we've got you on this journey, right? We've accepted that we've got refractory gold. Now, what do we do with it? You're interested. You've had a go at the Albion online calculator. You've typed in some numbers, and you think, hey, you might have a project here. Glencore Technology, we're more than happy to have discussions with you. We can talk you through previous projects that are running at the moment. We can do flow sheet design. We can take you on site visits. We can take you on 3D models, and we can show you what different things can be done. We're very proud of the lab test work that we do here. We can run you through all of these different test work results that we have. And also we pride ourselves on collaboration as well. This is your project and we want to be a trusted advisor, and we want you to be able to extract that metal inside and in country. So what does test work look like? What does that first stage look like if you're interested in that? For a very first test, we would require a minimum 1 kilogram concentrate sample for us to be able to do our first test. And that's probably between 23 to 30,000 US dollars. So that's, I think it's quite affordable for the amount that you get. And with duration to slot it into the laboratory schedule, we're talking between 8 to 10 weeks. And so what's going to happen? What would we do with your concentrate? We'll do some head characterization on it. So we'll be able to match up our numbers. We're going to be able to pass it through an isomill for some ultrafine grinding. And then we're going to be able to simulate the Albion process at a laboratory scale and see what kind of extractions we're going to be able to get. We can then pass it through a lime boil as well. If there's any jarosite or if there's anything going on where a lime boil increases gold and silver recovery, we'll also do that. And then we'll pass it through a laboratory scale CAL test to be able to show you what your gold recovery and silver recovery will be. You're going to receive a test work report and then also a class 5 engineering study as well. So that's going to have plus or minus 45 CAPEX and a similar estimate for your OPEX as well, for you to be able to decide, whether you want to progress and for you to be able to see, what it would look like to produce metal in country. Here, if you want to take a screenshot, we have a very active and good YouTube channel with lots of different webinars. We also have it in different languages if you're a native Spanish speaker, and you can look through our different processes, our different technologies, and then you can learn a little bit more. But there, please reach out in the comments if you have any questions or on LinkedIn. But yeah, looking forward to some questions and discussions. So thank you very much for your time.
All right. Well, thank you very much, Andrew, for the presentation. Just a reminder for attendees to type your questions into the question box in your GoToWebinar control panel. And I see that Lori, you've been able to join us. Great. So thank you. So yeah, questions. First of all, do you have a scale-up factor for the Albion process to go from laboratory tests to full-scale operation?
Yes, absolutely. That's a good question. So all of the parameters that we get from our laboratory scale tests, I think I showed you a picture of our reactors that we have on scale. All of the parameters that we get from those tests are all that we need to scale up to a full scale. So Glencore Technology is able to provide a full process guarantee from those bench scale tests. We have certain clients which have certain internal requirements, and they require them to put them through a pilot plan. And so we have those options as well, and we can also give you those options to do that. But that's not necessary from our side. That would be something for a client. But yes, from the bench scale tests, we can do full scale up and a process guarantee.
Okay. And you mentioned you have test work facilities. Where are those test work facilities located? Are there multiple that someone could?
Yeah, absolutely. Yeah. So if you're in the Asia Pacific region, or if your ore deposit or your operation is there, so we have core resources here in Brisbane, Australia, where me and Laurie are located. But closer to home for those watching at home, I'm SGS Lakefield in Canada, and then for those in North America as well, there's also McClelland's in Nevada as well. So they're also accredited to do Albion test work. Watch this space. We're currently onboarding new laboratories in Latin America, and so we're looking forward to having Portuguese speaking for Brazil and Spanish speaking in Peru and in Chile. So expecting those soon as well.
Okay. And can you give us a sense of where some of the commercial mines using the Albion on refractory gold mines are?
Yeah, so I would say that our flagship one is GPM or GeoPro Mining, and so that's currently operating in Armenia at the moment.
Okay. Any in North America at this stage?
No, not at this stage. But
Okay.
we would love. We are working on some certain amount of projects on that. Yes.
That's why we're here. Okay. Now, if someone's interested in conducting some Albion process test work with you, do you have to send it to you in Australia?
No, so you can send it to any of those labs that I mentioned, so SGS Lakefield, McClelland's in Nevada, and they'll be able to do those tests. So depending on export requirements or simply just to reduce the cost of transport, you can send it to a lab that's much closer to you.
Okay, great. What experience do you have with alkaline refractory deposits that are high in tellurium?
Laurie, would I be able to ask if you know more about this one?
Yeah, look, we probably don't have a lot of examples to go with, but the ones that we do have to go with, tellurium doesn't impact on the Albion process part of the gold recovery. So yeah. So I probably don't have any specific results to recite off the top of my head, but we have looked into tellurium, and we don't typically see any issues with the gold recovery and tellurium. I should add to that the lime boil on the end of the Albion process, we would often look to apply when there is tellurium present, and that can help us get a little bit higher recovery and break down tellurides and whatnot. But no specific issues I don't expect.
Okay. And can the Albion process be used for any other applications besides treating refractory gold?
Yes, absolutely. So it does also have a strong base in base metals, so in commercial operations. So zinc particularly, but also for other base metals like copper and zinc. And then we actually have an online calculator for copper as well on the website. So if you click on that link or go into the QR code or look around our website, if you have a copper deposit, you can have a look for an Albion process for copper.
Okay, great.
I might just add a little bit to that if I can, if that's okay.
Please do.
So not only base metals, but polymetallic concentrates as well. So if you had concentrate that had both base metals and precious metals, the Albion process is suitable for that. So usually with base metals and precious metals, we'd approach them differently. The base metals would be an acidic Albion, and the precious metals would be a neutral Albion. But in the cases where you had something polymetallic, we would approach that under the acidic conditions. That slows down the leaching of the precious metals sulfides, but they still will leach. So we get the base metal sulfides leaching first, followed by the precious metal sulfides, and then it's just a matter of solid liquid separation. Then base metals would go with the solution side of things, and the precious metals would stay in the solids, and then go forward to the CIL for recovery, and then whatever downstream for the base metal recovery.
Okay. Does high altitude affect the Albion process? For example, higher oxygen requirements?
Yes, no, that is a very good question. Yes, so for any deposits in Latin America, Bolivia or something up in the Andes, so we know that lower atmospheric pressure causes a lower boiling point, right? So that will impact our reaction kinetics. And this is all explored in our test work in engineering, so it's all a known thing. And so what this may result in is probably that the overall reactor size volume is going to increase, and maybe we'll need to attach an extra reactor on at the end. But that's also a strength of the Albion process as well, and its modularity. If you need to put an extra tank in there, if your feed throughput increases, you're able to add extra modules onto that. Oxygen is sparged on the sides, so it's sparged in at hypersonic speeds or higher than Mach 1 through the sides of the tanks. And there is the head of the hydrostatic head of the liquid above that. So if you're operating at high altitude, you might need to spend more OPEX to pressurize that oxygen to overcome the hydrostatic head in the mountains. But there's no impact on the oxygen utilization per se.
Okay. And do you provide any specialized training for the Albion process?
Yeah, absolutely. So, if you decide to build a plant, we have technology transfer programs for our clients, for their technical teams and for their operational teams. And Glencore Technology can organize site visits. So you can visit one of our existing clients and commercially who are using the operation, and you can use that to upskill, and you can use that to learn before commissioning so that you can ramp up quickly and faster. So an example of that would have been geopro mining in Armenia.
I think you're on mute, Ryan.
Sorry, no more questions on this end. So I thank you both for your time. I don't know if there's anything else you wanted to add. But if not, again, we've got your details, Andrew, for the paper you mentioned, as well as any other questions that anyone might have related to this. So thank you, gentlemen, both of you.
I just wanted to put on one more thing
Yes.
for the question about the tellurium. If you want to reach out, please do, and I can dig up some papers and make sure we get that sent through to you. Hopefully, answer that with a little bit more detail.
Great.
Okay. Well, thank you very much. Thank you, Ryan. Thank you, Andrew. Thank you, Laurie, for that very interesting presentation. I'd like to thank all of our attendees and ask that you please fill out the short survey that pops up on your screen at the close of the webinar. A link to the video recording of this webinar will be emailed to you tomorrow. For more online presentations like this one, visit the CIM calendar of events at cim.org. We look forward to seeing you at our next Solutions Exchange webinar. Have a good evening to all of you on this side of the world, and have a good day for you in Australia. Thanks very much, and that's it. Bye.
Thanks for sharing. Thanks,
Thank you all.
Bye.
Appreciate that.